maximal interval of existence. So we just, okay, so let's consider this interval. So here is this one. So right now we want to claim that this is the largest, actually maximal interval of existence, right, after our construction. But we haven't checked. We know this is an interval, which is a superset of all those intervals, right? But let's see whether there is a solution for every t. Yeah, whether there is a beta for any t from this interval, whether the solution value is defined, is well defined. So let's So next one, just verify. Just in the proof, you just need to verification, right? For any t from this interval. So just pick any t from this interval. Okay, let's see how can we define the curve. Okay, so yeah, so certain t can be less than s or bigger than s, right? So if it's less than s, what happens? So this is the first case. If t is less than s, t is less than s. Look at the t. Yeah, so by the way, t is actually bigger than L, right? Because it's in this, that means t is less than s, although less than s. But still it's bigger than L, right, in the interval. So you just pick any t, which is from this interval. So because it's bigger than L, remember the infimum. What's the definition of?
You can find an A that is less than t.
Yeah, so if this is a little bit larger, because this is a lower bound, but this is the greatest lower bound, right? Greatest lower bound. So lower bound, that means if this t is slightly bigger, then since t is bigger than L, and L is the infimum of all the left endpoints. You can find an A. Right, there exists an A. Because that's the infimum of all A's. So there exists an A such that A is less than
T.
Yeah, T, correct. Yeah, T must be bigger than A. Yeah, must be an A such that A is less than T. Correct? Yeah. And then So we just choose that interval. So there must be an interval with this left end point, right? So once you find an A, there must be an interval associated with this A. So we just pick that interval. Next, we will use an interval. Yeah. So that is as long as the left point is this point. So we just pick this one. So for this interval, we know this is an interval where there's a solution, right? Yeah, so then on which, we know we use this interval on which solution is beta. Yeah, so let's use this notation. This is a solution on this interval. So this solution certainly is from this interval to Rn, or some subset of Rn, right? So this one will go to the subset of Rn of the initial value problem. The solution is this of initial value problem. Yeah, so now we just use that solution to evaluate, to get a value at t. Okay, so what is that solution beta t? Is well defined, right? So we can have a value at this t. Yeah, so under this condition, you want to ask yourself, so t is in this interval. Oh no, you find this, t is also in this interval, right? It is less than b. Why? Because t is, since
T is less than S.
S, yeah, t is less than S. T is now bigger than A, we know already, right? T is less than S, so S is less than B. So sure, t is also in this interval. So t is in this interval. So when for any t in this interval, we know this defines a curve, right? Exactly. So sure, we have a well-defined solution on this t, or whatever t before S. Okay, so that's the first case. So for any t in this interval, what if t is after S? Yeah, so the second case,
We'll do the same thing and replace
yeah,
it in supremum, right?
right, use the supremum of the set, using the meaning of supremum, then you can identify. So that's your exercise. You can try to give using the similar argument. Yeah, so second condition we can go through it quicker. So what if t, but the t before less than S, right? What if t is bigger than S?
Then R is bigger than T. And
R is the supremum of all the right points.
right. And
Yeah.
so it would be, how do you explain that?
Yeah, so
So
you
there
can
would be
look at this
such
way.
that
So t,
B would be bigger than T.
yeah, t is bigger than S, and t is certainly less than R, right? Because
Right.
t is a point from R. Yeah, so it's still from that interval. We are just looking at this largest possible interval, still less than R. But R is the supremum, right? R is supremum. So if a little less, there must be an upper bound. Yeah, which is yeah, so B. So for any slightly smaller value, there must be B, right? Since T is less than R, because T is from the interval from L to R. Yeah, T is less than R. And R is supremum of all the B of the red points. Is the set of red points, right?
So you can find
that.
the B
That
such
means you
that
can always find the one B, right? Such that
T is less than B.
T is less than B, yeah. So there exists at least one B from that collection, such that T is less than B. T is less than B. So now, for this B, now let's identify one B. This B must be associated with one interval, right? So you just find that interval with the endpoint B. So we can already find one interval. So let's use just a similar argument. So we just use the interval with this B as the right endpoint. So we use the interval we use an interval because it could be other intervals with the same endpoints, right? We just use an interval with B.
Yeah, but how do you show they're the same interval?
Yeah, I use the same notation, but it's just the one interval, whatever interval is nice, you have B as the right point. That's okay.
Okay, it doesn't have to be the same A.
The A, don't worry about A, because I just want to pick an interval such that this interval has a B as the right endpoint. Yeah. We use an interval AB with B being its right endpoint. So we don't really, at this point, we don't worry about A, because this is an interval where there is a solution, right? According to our definition, it's a collection of all the right points of such intervals where there's a solution. Somebody?
They're not
Oh, no.
his door.
Okay. So nobody here.
They're not in different.
They're not from Dr. Lambert's door. They're probably from
They're
Evan's door
not.
here.
Okay, so now we have found the interval because this is the interval where there's a solution.
Right.
Yeah, so then we can find the solution that's defined on this interval. So here, so if beta t is the solution of the initial value problem on this interval, then we define so we just simply define the curve on our solution to be beta t. Yeah. So because for this interval there is a solution, right? Defined on this interval. So now if whatever this solution takes at t, that's our solution. So that's our definition of the solution. This is we just define our solution to be this value. Yeah, so you can double check. You define this solution with this, but by the way, is t bigger than a. Yeah, t is in this interval, right?
So it has to be real.
Yeah, you can double check. Is t in this interval? T in AB?